Hello everyone. In this lecture, we are going to learn about how to design web plate for saddle support. Our flagship course is Master Static Equipment Design and PVElite and Master Welded Storage Tank as per API 650. We have curated courses to suit your learning needs, so do visit our learning platform on scootoid.thinkific.com.
So first we'll try to learn how to design that web plate. So now, before we design, we need to understand how it will fail. That will give you indication that what are the forces and what is the area upon which that force is getting applied and the stresses are getting developed. So anybody can think of what exactly how that failure will happen for the web plate. Okay. I have drawn the cross section, both the view, okay, to you. Now, how that web plate, we are talking about web plate, how it will fail. Buckling, bending, weight of the vessel. Yeah, weight of the vessel is the load, basically. So you have correctly identified the load. And is it only the weight of the vessel, guys, which will be acting as a load? If we talk about this Q, whether it is only the weight of the vessel or anything else also acting on it. Liquid weight, yes, wind or seismic, no? So there will be a factor of wind and seismic, means either of it, which will be having a vertical component. So we find Q with that. Okay, so there is a factor of wind or seismic, whatever is governing. So that the vertical load. So there will be longitudinal, transverse. So both are longitudinal, transverse are horizontal, but it has a component of vertical because there are two saddles, right? So if you are creating moment, so to restrict that moment, to counter that, there is a reaction for that load. Okay. So anyway, that we have spoken about in the earlier chapter where we have did the jig analysis. Okay. Great. So that is the load which will be coming on the saddle. So we are very clear about the load. Now, how that web plate will be failing, how it will fail. Shearing. What else? Bending. Okay. Compression. Yes. So one we can definitely say is the compression. Vertical load. There is area which is restricting. So compression. Okay. Now, definitely bending will also come into play. Now let us see. I'm pretty sure, okay, that none of you might have thought how it is going to fail. That basically the web plate. It's a very, very good concept. Okay, I think very few of you might have. If you have read, then definitely you might be knowing. Not because of lifting. Okay. So now see, because of this Q, can you see the type of force getting generated? Okay. One is in the radial direction. So the Q will be basically getting distributed. Okay. We are focusing on the web plate. Okay. Don't think about wear plate or base plate. We are focusing on the wear plate. So basically that Q is getting distributed. So at this complete bottommost point, it will have only one component which is going down. Okay. Now, if you move forward in the upward direction, you'll see the component in the horizontal direction that will keep on increasing. Okay. So basically, it will have combination of two different types of reactions which is coming on the web plate, which is basically the distribution of Q along the web plate. Okay. So now because of this force, okay, now this point, which you can see here, that is called the center of gravity of the saddle arc. Okay. That basically the web plate arc, which is made at angle 120 degree. This is the CG of it. Okay. We'll be calculating how, we'll find this value. But at this location, at the CG of this arc, at this location, there will be a splitting force. This horizontal component which we are talking about, which is there because of this vertical load, because of this angle, okay, there will be a splitting force acting in the horizontal direction. Okay, if you just try to visualize, if I'm trying to press, let us see this horizontal vessel, I'm trying to apply a vertical load. How it will fail? It will try to split, okay, split into two parts because of this force. Are you able to visualize it? Okay, I'll just draw it. So at this location, this white marker, it will try to split it from this. It's trying to split. So definitely, due to this vertical load, there will be compressive stress. Okay. But in the web plate, the governing criteria for this design is the splitting force. Okay, we'll be taking care of that vertical tensile force also, compressive force also. But the governing criteria for this is the splitting force, which first of all, it will create a tensile stress in which area. So basically, which area is failing because of the splitting? Can you tell me which area is failing because of the splitting force? The middle one. But how it will look like? The area which is failing, how it will look like? The right hand side which I have indicated. This is how it will look like, right? If I take a cross section at this location, can you visualize that it will look like this? Do you agree with me? That it will look like this. Yes. So basically, this is the area which will be taking load of this splitting force, okay, in tension. Okay, so it will try to create a tensile force. Definitely, there will be bending also. We'll calculate that also. But the first thing is to calculate the tensile stress acting on this area because of this FH. So if I want to find that, the tensile stress, what I need to calculate first? That FH, the value of splitting force, right? What I need to calculate second? The area, which you can see here. This area I need to calculate, which is simple, right? We can calculate this area very easily. So only problem will be to calculate the splitting force, which we'll see how to calculate that. So once we do that, we will be able to calculate the tensile stress because of this splitting force. Okay. Good to go. Now, so first we saw the tensile stress, and definitely you can feel that it's basically shearing because of bending. Okay. So bending plus tensile both are acting. So we need to calculate the bending stress also, which will be acting again on the same area. Okay. So bending plus tensile, these are the two types of stresses which are governing in the design of web plate. Okay. See, understanding the philosophy or the failure is more important than knowing the procedure. Procedure, you can find, it's easy to follow that, but visualizing the failure is more important, by which force and which area which is failing. Okay. So if you understand that, it will be very easy to calculate also. Okay. Now, so the first part of design of the web plate will be to calculate the tensile stress, right? So we know that tensile stress will be FH divided by that area which you see in the right hand side. That is the area which is failing. So which we can definitely calculate very easily. The calculation of FH is what we will like to see. So now the FH is also very simple. It's a K1. There's a coefficient multiplied with Q. Q is your load, which you already have. It is due to operating weight plus wind or seismic added. Okay. So basically the reaction given by that saddle. So reaction force coming on the saddle. So K1 into Q. Q we already have. Now we only, if I'm able to calculate K1, we will be able to get that splitting force also. Okay. Now you see the formula of K1. So K1, if you see, basically depends upon your saddle angle. Okay. So here the saddle angle is theta. Now you can also see a beta angle. Anybody can tell me how to calculate beta? If you have beta in terms of theta, can you write? Or I'll make it even further simpler. What is the typical value of theta? What is the typical value of theta? 120 degree. So if the angle is 120 degree, that saddle angle, what will be the beta value if I take 120 degree? So basically, it's very simple, right? If we talk about this angle, we typically take 120 degree. In saddle, that is what we start. So half of that theta will be 60 degree. So if this is 60, if this angle is 60, what will be this angle? Because this total is 180. So this will be 120, right? Clear? Great. So beta is nothing but. So now with this, so this K1 basically depends upon your saddle angle. Okay. So if I have that, K1 is very easy to calculate. Okay. And once K1 is known, we know that multiply that with Q and you'll get FH. Okay. So area is also already known. So we'll be able to get the tensile stress, which is acting where that saddle is getting split. Okay. So now what should be the allowable? See, we have the stress, but I need a allowable to compare with. Okay. Now I cannot go to code and take the allowable of code, right? Because these are not pressure items. Okay. Whether saddle design is covered by ASME? Whether saddle design is covered by ASME? No. So allowable stress is basically 0.6 time of SY. Okay, 60% of SY is considered allowable for a non-pressure part. Okay, for tensile. Okay. For bending, we typically take 2/3 of the SY. Okay, 0.6667. Okay, great. So this is allowable. We have the tensile stress already. So just compare if it is coming within this value. Good. We have designed it. Great. So is the web plate designed? Is the design complete if I just do this activity, or something is left? The bending part is still missing. Okay. See, the temperature and all, we typically take room temperature. We don't consider high temperature because typically it will not increase much. But if it is given, then definitely you can take whatever temperature. But typically for saddle support, we always take room temperature. Okay? So if it is insulated, then your temperature may be higher. Great. So one part is over, but the second part, bending, is not over. Okay. So tension, we checked. If it is lower than SA, we are safe. Now let us talk about bending. Okay. So again, bending will be because of this FH. Okay. FH is trying to separate your saddle. Okay. So FH we already know. Okay. Because of that FH, we can calculate the moment, right? If I'm able to get the distance of FH, okay, which is not known till now, we have not calculated that. What is the distance where FH is acting? Okay. So if I know that, I can multiply FH with that distance. That will give me the moment. Okay. Now, what is C? C is the centroid. Centroid of the area which is failing. Okay. C is nothing but centroid of the area which is failing. We'll calculate that. I naught is the combined moment of inertia. Okay. Both of these terms you need to understand carefully. See, M is easy. Calculating M is easy. FH we already calculated. D is the distance where that FH is acting. Now here, the calculation of D is very important. Okay. So for that, this is the formula. D is equal to B minus R sine theta by 2 divided by theta by 2. Basically, theta is equal to L by R is used here. Okay. To calculate your D value. Okay. Where your centroid of this arc will be lying basically. Okay. So that is the D value. Use this. You'll be able to get the D value. Theta you have to take in radians definitely. Okay. B is the distance from center to the bottom of the base plate. Okay. And R is definitely the radius of the shell. Okay. Inside. Great. So if D is known, definitely we can calculate the moment. Okay. Now, what next? Centroid. Which area centroid I want to calculate? Which centroid basically I need to calculate? This, no, the cross section which is failing. This is the cross section which is failing, right? The blue color. Okay. So basically the blue color, but your wear plate, your even the shell. Okay. See, we are manufacturer. Okay. So any design is done on the considering the manufacturer's perspective, right? So any advantage is there, definitely will take. Okay. So if the splitting force is trying to split even your cross section of shell, the top part, that will also participate in preventing, isn't it? Do you agree with me? That this shell portion, now what length will be participating, that is a different thing. We'll talk about that. Okay. So this, which I highlighted just now, that is your shell. So basically that is the part of shell which is resisting. Okay. Now the second is your wear plate. Definitely that will be taking part than your web plate. Okay. So we are calculating web plate, but all these parts, all this cross section will play an important role in resisting. Okay. So they have to be calculated. Okay. Now, so here the next question will be to find X. What is X? What we call it? What we call it? Decay length. Yeah. So it's you can call it stiffening length, but that is not the exact, the stiff. It will be very subjective to that part. Like for stiffening ring also we calculate something like this, right? And the exact formula is there. So it's basically 1.1 under root dt. But if you break it, the d, if you write in R terms, you will get again 1.56 under root RT. Okay. So if you remember, stiffening, when we calculate along with shell, we take some part of shell, isn't it? How many of you remember that? When we take the shell also acting as a stiffening. Okay. So when combined moment of inertia, we calculate along with shell, we take this X, which is basically a decay length, but that is considered participating. Okay. Now, if just give you a little bit, insight, just for visualization, what exactly we're talking about. See, if this is the vessel and it is getting supported, definitely you will feel, that this area will be experiencing some of the stresses. Do you feel that? See, up to some length, there will be effect of this support. Okay. After that, maybe this point will not have any stress because of this support, but up to some length, definitely there will be some stresses. Do you agree with me? Or are you able to feel it? So do you feel that where we are supporting, after that, definitely up to some distance, still that shell will feel that stress, because of that support. So that is what is basically your decay length, where that is, influencing, that load is still influencing that part. Okay. So if the x is known, now we know how to calculate x. X is basically under root 1.56 under root RT. Okay. So once we know this x, h, we already know h is nothing but the width of your wear plate. Okay. So now can you calculate the centroid of this combined area? If you write a tabular form, it's very easy. Just find the area, multiply that with y. Okay. So Arun is asking what is T? Where I have written T? Under root RT. Yeah. T is the shell thickness. Sorry. Okay. Yes. Arun. Okay. So T is the because we are talking about shell, right? Remember? So under root R is also of the shell. T is also of the shell. Thickness of the shell and radius of the shell. Okay. Great. So that is the under root RT. Okay. Great. So if you have to calculate this centroid, first what we'll do? Calculate the area of the first item, y. Y is nothing but the distance. Okay. Then you multiply that, a into y. For the second item, again, you will do a into y. Okay. So you do with all the area. Okay. And then you just add all the ay and divide with the a. So summation of ay divided by summation of a, that is your centroid. Okay. So we can calculate centroid. So we have calculated the second term. Okay. Yes. So yeah, definitely we'll repeat y. See, y is basically what? No, if let us, it will come again in the second slide. Okay, don't worry. Okay. So decay length we already spoken about. Okay. So here 0.78, if you take both, it will be basically 2 times of it. Okay. So one side 0.78, if you multiply to 1.56. Okay. So this we already spoken about. RM is the mean shell radius, T is the thickness. Okay. Now I'm calculating moment of inertia. Now let us make it very simple. Okay. How we calculate moment of inertia? If this is my a rectangular part, what will be my moment of inertia? BDQ by 12. Okay. First, we need to know what is the axis along which I'm talking about, right? Unless we know the axis, how you can tell what will be my moment of inertia, right? Because it's always related to the axis. Okay. Let us take this axis. Now, can you tell me what will be my moment of inertia about this axis? dBq by 12, right? The the edge which is on the both side, which is perpendicular to that axis, that is basically the q. Okay. So it will be dBq by 12. Okay. Getting it? We always remember BDQ by 12, BDQ by 12. So, it has come here also. So are you guys okay? Have you got it? Okay. So dBq by 12. That is the answer. Okay. Clear? So basically the moment of inertia along this axis is dBq by 12. Now I'll ask the next question. What is the moment of inertia along this axis? The, axis 2, which is x distance away. What will be the moment of inertia of this shape about this? Use the same terms. Already, x value is given. The distance of that axis is given. So can you write the moment of inertia of that shape along with second axis? Can you write it? Area is A. So AX square plus whatever original it was, dBq by 12 plus AX square. Everybody agrees to that? Yes, guys, come on, respond. So basically, I1, which is basically your dBq by 12 plus whatever is the distance, the square of it multiplied with the area. Okay. So dBq by 12 plus ax square. Okay. So that is the moment of inertia along this axis. Okay. Now this is what we are going to use it very extensively in the inertia calculation, the combined inertia calculation, basically. Okay. Now, what is y in this figure? What is y in this figure? The centroid which we calculated, and also will be using that b by 2. Absolutely right. Y is nothing but b by 2. Okay. So because we are talking about this axis, so why we are considering about this parallel perpendicular to this axis. Okay. So now it will be again clear why I'm talking about y when we go to the next, the combined moment of inertia. Okay. So what we'll be doing, shell, the first item is shell, the topmost, the area of that multiplied with, means y you will write first, then you will multiply a, the area, into c1. C1 is basically your c, the centroid distance. Okay. C minus y. Okay. So basically that is your distance. Okay. Now, if I can show you, yeah, in this figure, it will be very easy. So what basically we are trying to do is that we are trying to calculate the moment of inertia of the shell. Okay. Let me just draw it for you. Okay. I'll use a black color. Okay. So this is my shell. Okay. So first I'll calculate the moment of inertia along its vertical axis. Okay. Means this line. Okay. Which is at y by 2. No, if I'm taking starting from this distance, so y by 2. Okay. So first I'll be taking the moment of inertia along this axis. Then I'll be moving it to this axis. Okay. Up to c distance we'll have to move, right? So a multiplied with exactly this distance. Okay. So what is this distance? Nothing but c minus y. Okay. Because this small distance is y, which is b by 2, thickness by 2. Right. So say if you write in Excel sheet, it will be very easy. So calculate individual areas and then shift it to the centroid. Okay. That is what basically we am doing. Okay. So yeah. Now, if I make an Excel sheet like this, it will be very easy. Find A, then find Y, multiply that A with C minus Y. No, now Y, and then square of it. Okay. And this is individual inertia, which is nothing but BDQ by 10. But remember, what is the width, along which it is rotating? That will be the Q. Okay. Along the side, which is the shape is rotating. So remember that while calculating inertia. Okay. And then you add I plus AC by C1 minus Y square. You'll get the inertia of the shell along the centroid. Okay. Now we do it for all the different items, and then we do the summation. We have got the total combined moment of inertia. Okay. Now, again, back to the bending stress formula. If you remember, M into C divided by I, the combined moment of inertia. Okay. Now we have all the terms. We calculated first M. We calculated the centroid. We also calculated the combined moment of inertia. Now I have the bending stress. Okay. Now I need allowable. How much I'll allow the bending stress. So that typically for non-pressure parts, we take 0.66, 2/3 of the yield. So 0.66 of yield is the allowable. So you just compare it with that. And if it is less, then your design is safe. Okay. So by doing these two calculations, you have qualified your web plate. All the items are not designed. It's only web plate which is designed till now. Making sense?
For in-depth training, and to learn more about these courses, register with the link in the description.